The journey of plywood does not begin inside the factory walls, nor does it start with machines or production lines. It begins far earlier, deep within managed forests, where trees grow slowly over decades, absorbing sunlight, water, and nutrients from the soil. These forests are carefully planned environments, where trees are selected not only for size but for straightness, density, and consistent grain structure. Forestry experts monitor growth cycles to ensure that harvesting is done responsibly, allowing new trees to replace those removed. By the time a tree is ready to be cut, it has already become a valuable raw material shaped by years of natural conditions. Once harvested, the logs are cut to standardized lengths and transported to the sawmill using heavy-duty trucks. These vehicles carry massive loads, often weighing several tons, and arrive continuously to keep the factory running without interruption. As the trucks enter the sawmill yard, the first phase of industrial transformation begins. The yard itself is a carefully organized space designed to handle large volumes of timber efficiently while preventing damage to the logs. Before any processing occurs, each log must be evaluated. This inspection phase is critical because the quality of the final plywood depends heavily on the condition of the raw material. At this stage, both human expertise and advanced technology work together. Skilled workers visually examine the logs, looking for visible cracks, decay, insect damage, or irregular growth patterns. At the same time, automated scanning systems analyze the logs using lasers, X-rays, and moisture sensors. These systems measure diameter, length, internal density, and moisture content, creating a digital profile for each log. Moisture content is especially important. Wood that is too dry can crack during processing, while wood that is too wet may cause bonding problems later during gluing and pressing. By analyzing moisture levels early, the factory ensures that each log is directed to the most suitable processing path. Some logs are ideal for face veneers, which require a smooth, attractive appearance, while others are better suited for core layers that focus on strength rather than looks. After inspection, the logs are sorted into large stacks based on species, size, and intended use. Softwood logs such as pine or spruce are commonly used for construction plywood, while hardwoods like birch or poplar are reserved for higher-grade panels used in furniture and interior applications. This sorting process allows the factory to maintain consistent quality and maximize yield from every log. The next crucial step is debarking. The bark that covers a tree serves an important purpose in nature, protecting it from insects and environmental damage. But in plywood production, bark has no structural value. If left on, it can contaminate machines, interfere with cutting precision, and reduce veneer quality. To remove it, the logs are fed into powerful debarking machines. These machines use rotating drums lined with steel ridges or high-pressure water jets that strip away the bark while leaving the wood underneath intact. As the logs rotate and move through the debarker, chunks of bark fall away and are collected separately. This process reveals the clean, smooth surface of the wood, making it ready for further processing. The efficiency of modern debarking systems ensures minimal loss of usable wood, which is essential for maintaining profitability and sustainability. The removed bark is not discarded as waste. Instead, it becomes a valuable byproduct. Many large sawmills operate biomass energy systems that burn bark and wood scraps to generate steam and electricity for the factory. This closed-loop system reduces reliance on external energy sources and minimizes environmental impact. In some cases, bark is also processed into mulch, soil conditioners, or other commercial products. With the bark removed, the logs are now prepared for conditioning, one of the most important steps in the entire plywood production process. Wood is a natural material with internal stresses and varying fiber structures. If processed in its raw state, it can split, crack, or produce uneven veneer sheets. Conditioning solves this problem by softening the wood fibers through controlled heat and moisture. The logs are transported to large conditioning vats filled with hot water or placed inside steam chambers. Here they remain for several hours, sometimes even longer, depending on the species and diameter of the log. The heat penetrates deep into the wood, relaxing the fibers and making them more flexible. This flexibility is essential for the next stage, where the logs will be peeled into thin veneer sheets. Temperature and time are carefully controlled during conditioning. Too much heat can weaken the wood structure, while insufficient heat may not soften the fibers enough. Sensors constantly monitor conditions, adjusting parameters automatically to maintain optimal results. This precise control ensures that every log reaches the ideal state for peeling. During conditioning, the logs also reach a more uniform internal temperature, which helps improve consistency across veneer sheets. This uniformity reduces defects such as uneven thickness, surface tearing, or grain separation. By the time the logs leave the conditioning stage, they are no longer just raw timber, they are precision-prepared raw material ready for high-speed industrial processing. Throughout this entire phase, sustainability and efficiency remain central priorities. Every step is designed to extract maximum value from each log while minimizing waste. Offcuts, bark, and sawdust are collected and reused, either as fuel or as raw material for other wood products. Water used in conditioning is filtered and recycled, reducing consumption and environmental impact. This early stage of plywood production sets the foundation for everything that follows. A well-inspected, properly debarked, and carefully conditioned log produces higher quality veneer, stronger plywood, and more reliable final products. Any mistake at this point can compromise the entire process, which is why the largest sawmills invest heavily in technology, skilled labor, and strict quality control. By the time the logs leave the preparation area and move toward veneer peeling, they represent the perfect balance between nature and engineering. Years of forest growth have been combined with hours of industrial precision to create a raw material ready for transformation. What began as a living tree has now entered a world of machines, measurements, and meticulous planning, setting the stage for the remarkable process that will turn it into strong, stable, and versatile plywood used across the modern world.
Once the logs have been carefully prepared, conditioned, and delivered to the core of the factory, the transformation from solid wood into engineered plywood truly begins. This stage is where raw timber is broken down into thin, precise layers and rebuilt through science and engineering into a material far stronger and more stable than natural wood alone. It is here that veneer creation and cross-laminated engineering define the identity of plywood. The conditioned logs are first mounted onto veneer peeling machines, massive pieces of industrial equipment designed to handle extreme weight and constant motion. Each log is centered carefully on rotating spindles, ensuring perfect balance as it spins at high speed. Alignment at this stage is critical. Even a slight imbalance can lead to uneven veneer thickness, surface tearing, or wasted material. Advanced positioning systems automatically adjust the log's orientation to maximize usable veneer and minimize core waste. As the log begins to rotate, it presses against a long, razor-sharp blade positioned with millimeter-level precision. The blade does not chop or saw. Instead, it continuously peels the log in a smooth, controlled motion, producing a long ribbon of wood veneer. This process is similar to unrolling paper from a roll, except the material is solid wood and the tolerances are incredibly tight. The thickness of the veneer is controlled by computerized settings and can range from fractions of a millimeter to several millimeter, depending on the plywood grade being produced. The peeling process reveals the natural grain patterns hidden inside the log. Growth rings, color variations, and texture become visible as the veneer flows forward. Operators and automated systems monitor the veneer as it is produced, ensuring that the sheet remains consistent and free from defects such as tearing, splitting, or excessive roughness. When the log becomes too small to peel further, the remaining core is removed and later processed into other wood products or used as fuel. Once peeled, the continuous veneer sheets are cut into manageable lengths using high-speed clipping machines. These machines operate with remarkable precision, slicing the veneer without causing cracks or fraying. The cut sheets then move onto conveyor systems where the next phase of quality control begins. At this point, veneer sorting becomes a critical operation. Not all veneer is created equal, even when it comes from the same log. Some sections are smooth, uniform, and visually appealing, while others contain knots, mineral streaks, or minor imperfections. Advanced optical scanners examine each sheet using cameras and sensors to detect flaws invisible to the human eye. Based on this analysis, the veneer is automatically graded and sorted. The highest quality veneers are reserved for face and back layers where appearance matters most. These layers will be visible in the final product, especially in furniture-grade or decorative plywood. Veneers with more natural defects are directed toward the core layers, where their visual imperfections do not affect the final look but still contribute to structural strength. Fresh veneer contains a significant amount of moisture, and before it can be glued and pressed, this moisture must be carefully reduced. The veneer sheets are fed into industrial drying systems that stretch across the factory floor. These dryers use controlled heat and airflow to remove moisture evenly from both sides of the veneer. The drying process is gradual and precise, as uneven drying can cause warping, curling, or internal stress. Inside the dryers, temperature and airflow are continuously adjusted based on real-time moisture readings. Sensors track how quickly water is evaporating, ensuring that each sheet exits the dryer at the ideal moisture level. This balance is essential. Veneer that is too dry becomes brittle and prone to cracking, while veneer that is too moist can compromise adhesive bonding during pressing. After drying, the veneer sheets are allowed to stabilize. This resting period allows internal stresses to equalize, reducing the risk of deformation later. During this time, additional inspection takes place. Workers and machines identify cracks, splits, or holes that may have formed or become more visible after drying. Repairing veneer is a meticulous but necessary process. Small defects are fixed using specialized techniques such as stitching cracks with fine threads, filling holes with wood patches, or trimming damaged sections. These repairs ensure that each veneer sheet meets the required standards for its intended layer in the plywood structure. Even core veneers, which are not visible, must maintain structural integrity to ensure the final panel performs as expected. Once the veneer is dry, repaired, and sorted, the factory transitions from material preparation to engineered assembly. This is where plywood becomes fundamentally different from solid wood. The defining characteristic of plywood is cross-lamination, a technique that dramatically improves strength and dimensional stability. Before layering begins, adhesive is applied to the veneer sheets. The glue used in plywood manufacturing is a highly engineered substance designed to perform under stress, moisture, and temperature changes. It must bond wood fibers permanently while remaining flexible enough to accommodate natural movement. The adhesive is applied evenly using roller spreaders or curtain coaters, ensuring full coverage without excess buildup. With adhesive in place, veneer sheets are stacked one on top of another. The key principle guiding this stacking process is the alternating direction of the wood grain. Each layer is placed so that its grain runs perpendicular to the layer below. This cross-grain arrangement distributes stress evenly across the panel and prevents the natural expansion and contraction of wood from causing warping or cracking. The number of layers in a plywood panel varies depending on thickness and intended use. Thin panels may contain 3 or 5 layers, while thicker structural panels may include 7, 9, or even more layers. Regardless of the number, the symmetry of the stack is carefully maintained. The outer layers mirror each other, balancing internal stresses and ensuring consistent performance. Automation plays a major role in this stage. Robotic arms and automated stacking systems handle veneer sheets with speed and precision, maintaining alignment and orientation. Sensors verify grain direction and sheet placement, preventing costly errors. Despite this automation, human oversight remains important, especially when handling high-grade veneers used for premium products. As the layered stacks are assembled, They form what is known as a plywood mat. At this stage, the mat is still fragile, held together only by wet adhesive and gravity. It must be transferred carefully to the next stage without shifting or misalignment. Conveyor systems designed for smooth, vibration-free movement carry the mats toward the pressing area. Cross-laminated engineering is what gives plywood its reputation as a superior building material. Unlike solid wood, which expands and contracts primarily in one direction, plywood's alternating grain structure balances these movements. This balance allows plywood to remain flat, strong, and stable even under changing humidity and temperature conditions. It is this engineered stability that makes plywood suitable for flooring, roofing, furniture, and structural applications. Every decision made during veneer creation and layering affects the final product. Veneer thickness, grain orientation, adhesive type, and layer count all work together to define strength, flexibility, and durability. By carefully controlling each variable, the factory transforms thin sheets of wood into a composite material capable of supporting heavy loads and lasting for decades. By the time the veneer layers are stacked and ready for pressing, the plywood already contains its essential structure. The natural beauty of wood has been reorganized through engineering, turning randomness into reliability. What began as a single log has now become a carefully designed assembly of layers, prepared to be permanently fused into a solid panel. This stage represents the perfect fusion of nature and technology. The organic grain patterns formed by years of growth are now guided by precise industrial processes, creating a material that is stronger, more stable, and more predictable than the tree it came from. The plywood is no longer just wood. It is an engineered product, built layer by layer to meet the demands of modern construction and design. Once the layered veneer stacks are fully assembled, the plywood enters the final and most decisive phase of its transformation. At this point, the material still resembles a carefully arranged stack of thin wooden sheets held together by adhesive biquets. But it has not yet achieved its defining strength or durability. The next stages, pressing, finishing, testing, and distribution, are where plywood becomes a finished industrial product capable of supporting modern structures across the world. The veneer stacks, often referred to as mats, are transferred to massive hydraulic hot presses. These presses dominate the factory floor, towering over workers and conveyors with steel frames designed to withstand immense force. Each press consists of thick heated plates that close around the plywood mats, applying extreme pressure while raising the temperature to activate the adhesive. This combination of heat and pressure is carefully calibrated because it determines the internal bonding and long-term performance of the plywood. As the press closes, the layers compress tightly together, forcing the adhesive to flow evenly across the veneer surfaces and penetrate the wood fibers. Heat accelerates the chemical curing process, transforming the adhesive from a liquid into a solid bond that permanently fuses the layers. Inside the press, the plywood undergoes a dramatic structural change. What was once a loose stack becomes a single unified panel with strength distributed evenly throughout its thickness. Pressing times vary depending on the thickness of the plywood, the type of adhesive used, and the species of wood. Thicker panels require longer pressing cycles to ensure heat reaches the core layers, while thinner panels cure more quickly. Sensors embedded in the press monitor temperature and pressure in real time, ensuring consistent results across every panel. Any deviation from optimal conditions can weaken bonding or cause internal stress, which is why pressing is one of the most tightly controlled stages in the entire process. Once the pressing cycle is complete, the press opens, releasing panels that are still warm and slightly flexible. These panels are carefully removed and placed on cooling conveyors. Cooling is a gradual process, allowing the plywood to stabilize as internal temperatures equalize. Rapid cooling could trap stress within the panel, leading to warping or delamination later in its life. By allowing the panels to cool slowly, The factory ensures dimensional stability and long-term reliability. After cooling, the panels move to trimming stations. Although the veneer sheets were carefully aligned during stacking, slight variations can occur during pressing. High-speed precision saws trim the edges of each panel, cutting them to exact standardized dimensions. This step ensures that every sheet meets industry size requirements, making it easy to use in construction and manufacturing. The trimmed edges also reveal the layered structure of the plywood, showcasing the cross-laminated design that defines its strength. Following trimming, the plywood undergoes surface sanding. Wide belt sanding machines remove minor surface irregularities, glue residue, and thickness variations. The goal is to produce a flat, smooth surface that is consistent across the entire panel. Sanding also prepares the plywood for further treatments or finishing, whether it will be painted, laminated, or used in its natural wood appearance. Dust generated during sanding is collected through advanced extraction systems and often reused as fuel or raw material for other wood products. Depending on its intended application, the plywood may then receive additional treatments. For exterior or structural plywood, waterproof coatings or sealants are applied to improve resistance to moisture and weather. Some panels are treated with fire-retardant chemicals to enhance safety in building applications. Others receive antifungal or anti-termite treatments, extending their lifespan in harsh environments. Each treatment is applied with precision, ensuring penetration without compromising structural integrity. At this stage, quality control becomes relentless. Even though the plywood appears finished, it must prove its performance under real-world conditions. Quality assurance teams select samples from each batch and subject them to rigorous testing. Some panels are bent under controlled loads to measure strength and flexibility. Others are soaked in water to evaluate moisture resistance and bonding integrity. In some cases, panels are deliberately broken apart to examine the internal glue lines and confirm proper adhesion between layers. These tests are not symbolic. They are essential safeguards. Plywood is used in critical applications such as flooring, roofing, wall sheathing, and furniture, where failure could have serious consequences. By testing panels under extreme conditions, manufacturers ensure that only reliable products reach the market. Panels that fail any test are rejected and either reprocessed or recycled, reinforcing the factory's commitment to quality. Once approved, the plywood panels move to grading and certification. Each sheet is assigned a grade based on factors such as surface appearance, strength, thickness tolerance, and intended use. The grade determines whether the plywood is suitable for structural construction, interior use, decorative applications, or industrial purposes. Automated stamping machines mark each panel with grade information, manufacturer details, and certification logos that indicate compliance with national and international standards. These markings provide transparency and trust, allowing builders, manufacturers, and consumers to select the right plywood for their needs. Certification also reflects the factory's adherence to responsible sourcing and sustainable production practices, connecting the final product back to its origins in managed forests. After grading, the plywood is stacked into large bundles and prepared for packaging. Protective wrapping shields the panels from moisture, dust, and damage during transport. The stacks are secured tightly to prevent shifting, ensuring that the panels arrive at their destination in perfect condition. Forklifts and automated handling systems move the packaged plywood through the warehouse and onto waiting trucks or shipping containers. From this point, the plywood begins its global journey. Some shipments travel short distances to local construction sites, while others cross continents to supply international markets. The same plywood panels produced in one factory may end up as flooring in homes, cabinetry in kitchens, formwork in bridges, or structural components in high-rise buildings. This versatility is a direct result of the careful manufacturing and quality control processes applied throughout production. Even after leaving the factory, the impact of these final stages continues. The strength, stability, and durability achieved during pressing and finishing determine how the plywood performs over decades of use. Proper bonding ensures that layers remain intact under load, while accurate grading ensures the material is used appropriately. The attention to detail in this phase directly influences safety, longevity, and customer trust. The final phase of plywood production represents the culmination of every earlier decision, from log selection and veneer preparation to layering and adhesive choice. It is where potential becomes performance. The combination of heat, pressure, precision cutting, and testing transforms engineered layers into a dependable building material that supports modern life in countless ways. As the last pallets are loaded and trucks depart the factory, the plywood carries with it more than just wood fibers. It carries the result of advanced engineering, strict quality standards, and a production system designed to balance efficiency with responsibility. What began as raw timber in a forest has become a finished product trusted by builders and designers around the world. In this final transformation, plywood proves why it remains one of the most important materials in construction and manufacturing. Strong yet flexible, engineered yet natural, it stands as a symbol of how modern industry can take simple resources and refine them into something essential, durable, and deeply integrated into the structures that shape everyday life.